Welcome to the presentation of Velociraptor, the next evolution for the RaptorX hierarchical caching solution. So my name is Vladimir Rodionov, and I'm the founder of the Carrot Cache, and I'm the major developer or lead developer of the Carrot Cache and the Velociraptor products. So my past experience mostly in the big data space. I'm an Apache software developer. I'm Apache committer. I'm a long-time contributor to the Apache NoSQL database HBase. I've done some major contributions, some major features, including the incremental backup and restore and the distributed compaction for the medium-sized objects. This is my quick introduction. Okay. Let's start. First of all, why do we need caching for in the Presto? So Presto is basically the distributed OLAP query engine, which actually separates compute and storage. And sometimes these separations can actually result in the longer query execution time high latencies, and if we need to support interactive queries with a sub 1 second execution time, so we need just to do something additional to make it possible. So our first approach was introduced in 2015 by Facebook. It's called Raptor architecture. So basically Raptor collocated compute and storage on a single node. So all the data has been distributed between the compute nodes, and each node has its own subset of the data set. This how they actually improve the performance. How they achieve interactivity for some queries, and it worked. Definitely, but of course it was shared nothing architecture, and so but the limitations were quite obvious in this approach. So low cluster utilization, low tail performance, because in case of the failure of one node, if it fails, so basically everything fails. High engineering overhead just to control the data distribution, to control the data ingestion. So which resulted in high operational overhead, of course, because if you write some additional scripts or programs to distribute and control the data, you need to execute these programs and scripts periodically, so you need additional stuff to support this. And of course, security vulnerabilities, because in this case now actually you need to take care not only single data storage, but the distributed storage itself, which is can be hundreds or maybe thousands of nodes in the cluster. So that's why actually the evolution of the Raptor was the next version of the Raptor, which is a RaptorX, was introduced in 2019, because just to to access actually and to remove all these limitations. So basically RaptorX separates compute and storage, of course. It uses local SSD as a cache. Yes, this was major difference. So now data is actually totally separated from the compute, but data can be cached partially on each compute node. And RaptorX introduced the 5 type of caches. It's 2 caches on the Presto coordinator node, which are metastore and file list, and 3 caches on the H worker node: fragment result cache, or Parquet data meta cache, and the IO data cache, which is a Luxor implementation. And this cache actually caches the most frequently used parts of the remote files. Usually these are ORC files or Parquet files. So there are some actually performance numbers which have been posted by the Presto community itself. And they show that RaptorX is better, at least on some queries, and it provides better average execution time. It provides much better the tail latency, and everything looked very good. So look good or not? So are there any limitations in the RaptorX as well? Yeah, there are. So 3 types of caches: metastore, file list, and ORC Parquet meta cache. They use Java heap to keep the data. So what does it mean? It means that you need to increase the Java heap space for every Java process in the system. What does it mean? It means that actually you can get some unexpected garbage collection pauses. stop the world pauzes. I mean, you can get the excessive garbage collection pressure when the garbage collection runs continuously and trying to release some memory. And this can result in some actually unexpected behavior. For example, so a couple years ago, the ticket was opened for the Presto, which is called Optimize Reading Protobuf Footers. So basically, what the problem was for the very wide tables, like 3,000, denormalized tables, like 3,000 columns, Facebook's discovered that if they do not cache the ORC meta information, they need to parse it repeatedly. And this parsing basically can take up to 40% of the CPU time. And of course, if you do not cache this information, you just need to retrieve it every time from the remote storage, and the latency increases and the query execution time increases as well. Okay, what happens if you cache it, or you try to cache it? It's basically, they discovered that just in their use case to cache everything they need to allocate 20 gigabyte of Java heap space to keep the data in the cache. And they discovered that it results usually in very high garbage collection activity, which actually decreases again query execution time. So either you have like high CPU time and high latency, or you have like high garbage collection activity and high latency again, and high CPU, of course, usage again. So what did they do? They actually disabled the caching for ORC meta information completely. So they do not use it in their clusters. Okay, what about the disk-based caches, like fragment result cache and IO data cache? So fragment result cache caches each object as a separate file. Okay, it's good probably if object size is measured like in megabytes or tens of megabytes. But what about if it's several kilobytes or several hundred bytes? So that's possible again. So you will end up with a very, very, very large number of objects in the file system. The same is true for the data cache as well. So by default page size to cache in the file system is 1 megabyte. So if you want to have a cache size like 1 terabyte, it means that you will end up with 1 million files in the file system. And this is the problem not only in the number of files. The problem is actually all the write operations going to be the random writes, because the write size is quite small. So when you delete small files or create small files in the file system, which is based on SSD, so you usually perform the random write. And random writes are bad. So basically, the random writes increases the device level write amplification. They results in excessive SSD wearing. And they results in the shorter SSD lifespan. Another limitation probably for RaptorX, it's only data cache is restartable. So contents all for other caches is lost when you restart Presto coordinator or Presto worker, and so you will get the cold cache after the restart. And most interesting thing, basically data cache is still not available as of current version of Presto 2.81. So because of some very strange bug in the implementation, actually. Recently it has been fixed, as far as I know, but it's still not in the release, and probably it's going to be in the next release of the Presto. But it means that it took more than 2 years to fix the quite a simple bug, in my opinion. Velociraptor. So what does it do? So basically it uses absolutely the same architecture as the RaptorX. It just provides the different implementation for all 5 caches: metastore, file list, fragment result, or C data and IO data. Okay, so now you can actually have every cache either off heap or, of course, no on heap caching at all. So we do not touch the Java heap space at all. All the caches can be either off heap or disk based or hybrid. It means that hot data can be kept off heap and the warm data can be kept on disk. So for all 5 caches. So Velociraptor is powered by Carrot Cache. Carrot Cache is the actually new development, and this very high scalable Java caching implementation. It supports billions of objects. It, of course, in case of Velociraptor, it supports extra-wide huge tables for meta information, like with millions of partitions and with thousands of columns. It can be run in 3 different modes of heap, disk, or hybrid. It increases SSD life by a factor of 30 at least as compared to RaptorX, and we will talk about this later, how it can be done, how it is achieved. And most interesting thing and most important, all caches are restartable now. So you can actually shut down your process, press the coordinator or press the worker, then start it up and you will get the warm cache again quite easily. And the load and save time is limited by available IO only. It's very fast. So the Carrot Cache, as I said already, supports different modes of operations: 3, RAM, SSD, and hybrid. It has very low RAM overhead for meta, so it requires only like 6-8 bytes to keep in the RAM to keep the object information. So because of this, it can support caching of small object on SSD. It provides full persistence and restartability. It provides continuously available performance. So what does it mean, continuously available performance? For most caching solutions out there, very well known, like Memcached or Redis, you will need to restart the processes periodically because of the internal issue, which is basically internal or external fragmentation of the memory. So they suffer from these types of issues, and they definitely do not provide you CAP, continuously available performance. So there is no guarantee that you will be able to run these servers for months or for years, definitely. That's a Carrot Cache. You can do this because Carrot Cache does memory allocation in very large blocks. So it doesn't allocate memory in a small objects. And allocation is done like by very large segments. So that's pretty much it. So it has a log structured storage design. It has a very low device level write amplification because it performs only sequential writes, and the device level amplifications is around 1 for the Carrot Cache. But the most interesting part, most interesting thing in Carrot Cache implementation, it's a very low application level write amplification. It means that, for example, it's way below 1. What does it mean? It means if you write, for example, 1 megabyte of data into the cache, it can actually write not 1 megabyte, but like 200 kilobytes, like much less than this. This is done because Carrot Cache uses a so-called admission controller. And admission controller is a pretty smart thing, which actually decide is this particular object worth caching or it's not. This is a high-level overview of the Carrot Cache architecture. Excuse me. Carrot Cache can be run in different modes. One mode is the standalone server, which actually provides the Memcache and Redis interface, and it can be run in the embedded mode, which is actually Velociraptor uses. So the most interesting and most important parts of the Carrot Cache architecture is IO engine. So IO engine is pluggable. There are 2 implementations, which are the off-heap based IO engine and the disk-based IO engine. So there it's possible to introduce some other implementation. For example, for the disk-based, we can do the async file IO implementation. The current implementation is synchronous, so all the read and write operations are synchronous. Or we can do it asynchronously as well, or we can use some kind of native API just to access persistent memory, which provided by Intel, for example, and implement the different type of AI engine. So the next one major component is memory index. So memory index is where we keep all this information, just which helps us to find the particular object in the cache. So memory index is very efficient. It requires very small memory just to keep the information for the object. It's like 6-8 bytes minimum, and it's pluggable, so you can provide your own implementation for the index format if you need some additional information to be kept with the index, for example. Garbage collector. So the purpose of the garbage collector is just to collect the garbage, or to collect the deleted objects, or to collect the object which has been expired, or to collect objects which have been evicted. So there is no, when object is evicted, it doesn't, caret cache doesn't do it directly in the memory or on disk. So it just marks this object as evicted. And later we need to run garbage collector to collect all this garbage and to rewrite data. Admission controller actually decides, do we need to admit the object to the cache or not. So it's a pluggable component as well. So you can provide your own admission controller, for example, like some machine learning stuff you can add to this admission controller for your particular use case. The default implementation works pretty good actually. It can reduce the write throughput to the cache by factor of 4, sometimes by factor of 10 for some synthetic workloads, with several percent of loss in the cache hit rate. So basically it provides quite comparable performance by writing much less data to the cache. Let's take a look at the examples which we briefly touched previously. This particular ticket, optimize reading protobuf footers, which we discussed already. So what actually Raptor does need and what Velociraptor actually does need to provide the caching for this. First of all, RaptorX can provide the caching, but it will require 20 gigabyte of heap space, and it results in very high garbage collection activity, very high CPU usage. So basically it makes the cache unusable. Or if you do not cache, so you will end up again with a high CPU usage, because you will need to parse all this information every time you access the ORC file. And of course, the execution time increases because you need to access the remote storage. So Velociraptor actually requires less than 10 gigabyte because data is serialized. When you serialize Java object, the size usually is less than object itself occupies in the Java heap space. So it's basically around 10 gigabytes, so you can keep it off heap. You have zero garbage collection activity, you have almost zero CPU activity, so it's absolutely doable with a Velociraptor. Let's take a look at another example. For example, how RaptorX can handle large denormalized tables. Yes, let's consider the next actually case. You have 1 million partitions. Yeah, it's possible. And you have very large white table, 3,000 columns. So, for example, if your table partitioned by day and location, you can easily end up with 1 million and more partitions. So in this case, to cache all the meta information for this particular table, you will need to cache at least 3 billion of objects. It's 1 million times 3,000. For every partition and every column, there is one single object, which is called partition column statistics. And you will need to cache 3 billion of objects. So average size of this object on heap is approximately 200 bytes. So for RaptorX, it will require 600 gigabytes of Java space. So absolutely impossible. For the Velociraptor, average size of heap is 100 bytes serialized, and Velociraptor requires 300 gigabytes of heap or disk, and only 24 gigabytes of RAM to keep the index. It's absolutely doable without any questions. The next example, your data cache. Let's consider that we need, like, for example, 10 terabyte of cache size. Why do we need 10 terabytes for? Yeah, probably we would like to cache everything, or we have a very large data set. Yeah, why not? So for RaptorX with a 1 megabyte page size, default page size, you will create 10 million files in the file systems. That's a pretty large number. And it will require 4 gigabytes of Java heap to keep the index information in memory. If you, for example, not every time actually 1 megabyte is optimal size of the data page. Sometimes you will need less than 1 megabyte because you fetch data randomly from the file, and the usual read size may be like several hundred kilobytes. It's possible, yeah, if you have a very wide table. For example, it's more optimal in this case to have 256 kilobyte page size. So yeah, RaptorX can do this again, but you will need 40 million files. You will have 40 million files in the file system, and you will need 16 gigabyte of heap space. So to keep the index, it looks like almost quite impossible. So in case of Velociraptor, with a 1 megabyte page size, we will have only 40,000 files in file system, and it will require only 80 megabytes of heap. For 256 kilobyte page size, the same 40,000 files in the file system and only 320 megabyte of heap. Even if we decide just to go with a 4 kilobyte page size, we will still have the same 40,000 files in the file system, and we will need only 20 gigabyte of heap space. Again, it's doable. The question is, do we need a 4 kilobyte page size? Probably we don't. But it just demonstrates the Velociraptor scalability. And again, Velociraptor provides up to 30 times longer SSD life because of the optimized device level and application level write amplifications. So to recap, actually, advantages of Velociraptor versus RaptorX. Velociraptor provides much higher scalability. It gives you much more options where you can keep your data in, so of heap, disk, or hybrid. It of course supports billions of objects because it has much higher scalability. It doesn't use Java heap at all. Its basically usage is very absolutely minimal. It doesn't provide any additional zero or garbage collection activity. So you can actually dedicate all your Java heap space memory for your query processing engine. It provides highly improved SSD longevity, and it can use more efficiently SSD for the data page cache. And of course, all caches are restartable now. So you can shut down your cluster, you can start it up, and you will get all your caches warmed and ready to go. Thank you for your attention. Folks, if you would like to participate in the beta testing, so there is some information on this screen where you can actually register. You can contact us or you contact me directly. You have all the email address on the screen. Thank you very much for your attention.